Welcome back to AP Pre-Calculus. This is lesson 2.3, Exponential Functions. So in Algebra 2, we started dealing with a lot of functions. Some of those functions you actually dealt with back in Algebra 1. But these three here are three of the ones that are going to show up a lot in this class and forward in calculus. And really, exponential functions is some of the most important functions in the real world, as they appear in a lot of growth models and a lot of decay models. So these are things that you're going to deal with if you keep going on in math for quite a while. All right, on this page, we're going to go over some of the key characteristics of exponential functions. Starting over here, we have the general form for an exponential function. F of x is equal to a times b raised to the x power. And b has got to be greater than 0. Remember, you can't have a base that is negative, and you can't have a base that is 0, right? And a and b are going to be constants, where a isn't going to be a 0 either. And b can also not be 1. If you remember from last year when we did exponential functions, we had some rules for our bases, because if it was 1, it would never change. Whether when we raise it to an exponent, it doesn't change. It's always going to be 1. So it doesn't grow or get smaller. All right, so over here, on this side over here, a represents the initial amount, okay? Meaning where we start, we're going to put a 0 in for x, that's our starting, and b represents the base, all right? If you remember from the last lesson, we also called it a common ratio. Okay, so exponential growth, as you move from left to right, starting at negative infinity, moving to positive infinity, it is always increasing. So an exponential function will always be either increasing or decreasing. It will never change. So we're not going to have any maximums or minimums. The relative in a local area is we're going to start low and go high, so we don't have a change. A decay model starts high and goes low, same idea. So when we are always increasing or always decreasing, remember we also have this thing called concavity. So when are we concave up? We are concave up when our rates of change are increasing. So if we wanted to write that out again with our rates of change, we could do that. So if you look at those red lines that I drew on there, those are the rates of change, the slopes at those points. On the exponential growth, notice that they are getting steeper and steeper in the positive direction, which means they are increasing. On the exponential decay, they start out really steep negative and then get shallower, which also means they're increasing. So in this case, they are both concave up, but they could be concave down if our A was negative and they went the other direction. All right, they'll never have both concave up and concave down because they only do one thing. And last but not least, let's talk about end behavior. So your end behavior is going to be when x increases or decreases without bound, one of three things are going to happen. You're either going to go to a positive infinity, a negative infinity, or a 0, okay? So if we look at this guy over here, as I approach negative infinity, my limit is going to be 0 because I start getting a horizontal asymptote idea out here. But as I go to positive infinity, my arrow goes up to positive infinity, right? And same thing over here for decay. As I move to negative infinity, I'm approaching positive infinity. As I go to positive infinity, I'm approaching 0, okay? So one of these three things has to happen on your end behavior, all right? You'll always have this guy over here. One of your sides will be going to 0, but these could go either way, depending on the makeup of our general form. What's going on with our A? What's going on with our B? All right, let's practice some limit statements real quick. So go ahead and pause the video, write in your limit statements, and see if you can answer these before I do. All right, let's see how you did. So on A here, we'll call that f of x. As I am going towards negative infinity, what's going on with my end behavior? Well, I'm flattening out, meaning horizontal asymptote, and I'm flattening out at 0. As I go to positive infinity, my value of y is going up to positive infinity. So we would write it like that. Let's try h. As I moved to negative infinity, I'm going down to negative infinity. As I move to the right on my graph, I start shallowing out and almost getting horizontal. We got a horizontal asymptote at 0. All right, this time we don't have a graph to look at, so we got to kind of think of it. You might want to sketch a little graph if you think about it and go, okay, what does this do? I know that I'm going to have a point up here at 5 because that's my initial value if I put 0 in. But when my base is less than 1, that is a decay model. So I'm going to be doing this kind of deal. And now we can answer that question. As I move to as I move to negative infinity, my graph is moving to positive infinity. And then as I move to positive infinity, I'm flattening out at 0. So my limit is approaching 0. And that's it. All right, let's move on to example 2 here. These are pretty easy, especially A and B. So I'm going to add a couple little things to that after I'm answer A and then answer B. So let's start with what they want. We're looking at this graph, and it's asking us, is this concave up or concave down? Like, if you want to kind of imagine finishing the curve and then starting to go back up, is that concave up or concave down? Hopefully, by now we all know that it's concave up, right? Second, is the function increasing or decreasing? And remember, when I ask if the function is increasing or decreasing, I'm just saying as I move left to right, am I going up or am I going down? So as I move left to right on this graph, I'm obviously going down, so that is decreasing. Now, the second part I want you to do, let's go back to this. That's what it looks like. We can answer something about A. We know something about A. We know whether it's positive or if it's negative. And looking at this one, what would we say? We would definitely say that it is positive. So A has got to be bigger than 0. What about B? Do we know anything about B? Well, we do. We know that it's got to be either in between 0 and 1 or greater than 1, right? Is this a growth model or decay model? Well, I'm getting smaller, so it's decay. That it means I have to be between 0 and 1. Why don't you pause the video and try B on your own? Okay, so looking at B, as if I were to complete that curve, we would be concave down. I don't really have to complete the curve to know that. You can kind of look at it, hopefully. And as I move from left to right, I am also decreasing again. So now, let's do that A and B thing again. What do we know about A and B? So this one's a little bit tough to look at and go, oh, that's a growth model or that's a decay model because it's a little bit weird. What do we know about A? We do know something. We know that it is less than 0. It had to be negative because it got flipped over the x-axis. So if we were to flip that back up to the, if I took away that negative, it would look like that. So if you look at that red graph, that's actually a growth model. So what do I know about B? B is going to be greater than 1. Now, since we did the A and B stuff over here on A and B, we can look at C, their A and their B, and maybe get an idea of what this looks like. Like, I do like to sketch a graph. It doesn't even have to be good. Like, I'm calling that 3. I don't even have anything on there. I'm just going to call that 3 because that's my initial value. So what do I know about this graph? I know that it has to be like that because it's positive, so it can't go into the negative part of my graph. And I know that my base is bigger than 1, so it's increasing the whole time. So now I can answer the questions of concave up and increasing because over the whole thing, I'm moving up. All right. All right, last example. Here we have a table, and we are wanting to determine if this function f could be linear, quadratic, exponential, or none of these. So how do we do that? First, we need to look at the x. To do this in table form, our x has to make jumps that are equal. So how is x moving? It better be the same every time. So from 1 to 6 is 5, 6 to 11 is 5, 11 to 16, 5, 16, 20. Okay, good. That side worked out well for us. So let's look at our jumps on the y side. That jumped 2, that jumped 4, that jumped, what is that, 8? And then that jumped 16. If those were all the exact same number, we would say that's linear. And we can actually do this again, meaning we could subtract again. If we subtracted those and got the same number, then we could say it's quadratic, right? But we're not going to get the same number, so we're going to erase those lines here. So it's definitely not linear because this is not the same. That would be linear. If my second one was the same, it would be quadratic, and they're not, so it's not quadratic. So is it exponential? And the answer is yes, because I am multiplying by 2 to get to the next number every time, right? So that is what exponential would do. So we would write this out. We would write exponential, if they asked to explain, exponential, and why? Because the average rate of change is proportional. Okay, and what does proportional mean? It means we're multiplying by the same thing over and over again. All right, and that's the end of this lesson.